Hello, can you hear me? Okay, cool. And is the audio okay, or is there some issues? Like, is it worse than last time? Okay, that's very nice. Yeah, so sorry for the delays. I had a few problems. Um, so hi. Oh, I need to enable the chat, please. Oops. Okay, nice. So then, hello everyone. So I want to start this a little bit faster than last time. It was a bit, but with the problems, I'm not sure. So, um, what I did last time, hello, we sent. Um, so in the last stream, hello, quantum developer. So in the last stream, we, mm, we created this small demo here. So originally in the SDL template, there was just a rectangle, and in the last stream we derived some 3D rotation matrices. So what we did basically was um, we don't have a transformation pipeline currently, so this rectangle just gets rendered in this normalized device coordinate cube, which is what OpenGL expects us to input our final transformation so that it can be mapped to the screen. And yeah, so we basically just um, captured the mouse input, and if the mouse is moved from the left to the right, and then we rotate the rectangle around the y-axis. So this is what you can see here. Here mouse motion, we use this mouse motion event. No, wait. Okay, so we use this mouse motion event to get the mouse position, and then each frame we compute the delta. And wait, can you see what I'm doing here, or is the, because it looks like the screen is frozen? I'm not sure. Okay, that's a bit weird. Uh, I'm not sure what to do about this. I mean, the chat worked, right? Oops. Okay, I think now it works. Okay, then maybe I can start over. So, in the last episode, like I said, and then has stream, we originally we just had this rectangle here, and we render this into the normalized device coordinate cube like OpenGL expects, and when the mouse is moved, we rotate this around the y-axis and in the other direction, like around the x-axis. And this works like here. We define a mouse delta, so we know how far the mouse moved in one frame. And with that, we can increase the angle for the rotation. And when we move the mouse in the y direction, we rotate around the x-axis. That's why I increase the x angle. And with the x, when moving in x direction, we rotate around the around the y-axis. Yeah, and then with these angles, we can create a rotation matrix for the rectangle. So basically, we wrote these two functions, or even three, where we can rotate around any axis. I mean the x, y, or z axis by an angle, and then we can combine these by just multiplying these. And what we need, so what I want to do today, because rendering everything in this frame here is is a bit bad, I could say, because it's not clear. So the edges of this cube, I this time I even looked up how the coordinate system of this cube looks like. So this is the NDC cube where we are currently, and so we are looking from this direction into this cube. So if something is here, it would be on top of something that is here. And yeah, so this is a left-handed coordinate system, but that doesn't matter. Actually just wanted to say, what we want to do is, because we are rendering everything in this cube here, which is not really intuitive. And also you don't really know any units, because everything is in this cube. What if you wanted to scale an object, or like you can't really show any units here, use any units. So what is done, what you typically do is you define a world system. So this is a world, this is your, you can think about it like your game world. And here you have like units. So for example, this cube here has a side length of 2, and you could, for example, say that's meters. And so you can imagine this just like the world we walk around in. So basically here's the unit coordinate system. Maybe I can remove this. So here's the x-axis, here's the y-axis, and here the z-axis. And no, wait, this is a, so it's a right-handed coordinate system. And now what we want to do, we want to we want, first of all, because we just have this world here, it's just a static description of what is in this world. And what we typically do is we define a camera, so we can move the camera around and yeah, define what exactly we are looking at in this world. So this is much more intuitive than maybe thinking about this here. And this camera consists of two components, I would say. So first of all, we have a coordinate system for the camera, like where the camera is and which direction it is looking at. And again, here and here. And the camera is always looking in the negative. So this is the z direction, and the camera is looking in the negative z direction. And then the camera also has like a view frustum. I don't know if you can see this really well, but this is these black lines here. It's like a, so it looks like a pyramid. So maybe I can draw this out here. Wait. I'm not sure if you can imagine what I just draw here, what I just, but so it's basically like a cone, but you just define this to be, we can see this here. Yeah, it's a truncated pyramid. I don't know how to pronounce that. So, and in 3D it would look something like this. Yeah. So that's the two components of the camera. Like first, it has a position and orientation. So this is what is encoded in this coordinate system here. And then we can also define like how much so this is just the position and the direction in which we are looking, but how much, so for example, if you would look at this from the top, so if here's the camera, Like, for example, you could just see this part here of the world like this, or if you would define it in some other way, you could see this this part of the world. And that's the view frustum that we need to define. And each of these parts is like one step in the transformation pipeline. Because the way this is now, the way these two things are now converted into this cube here is first, you can think of it, we transform the world. So this here is applying step 1, the position and orientation of the camera. And what this does is, after this step here, the coordinate space of the camera is now the unit coordinate system. Wait. So this here is now and while previously this was the world origin. And yeah, so basically we just make this coordinate system be the initial coordinate system with this first transformation. And the second transformation, so you can see then here we have the view frustum in the like lying somewhat in the origin, and the next step is then to apply the view frustum, and this just converts the view frustum into this cube here. And yeah, that's the basic idea. And if we implement all of this, yeah, so before I implement this, I would start with this one. The problem here is it's really hard to see intermediate results, because like you can't see just this step. You have to implement everything, and in the end you just have to pray that you did everything correctly. um, so yeah, so we would start with this step here. But before I do that, I want to give some more intuitions about the matrices here that are involved, because I think this makes it a bit easier to think about this stuff. Um, okay, so because first of all, you might ask yourself, okay, because matrix multiplication is not commutative, so if I change the order here, you could ask yourself what this exactly changes. And I'm not sure if I can visualize this here, because this is a pretty simple example. But what you can think about is, if you have some matrix A, if you apply another matrix like and with apply, I mean multiply it from the left or from the right. If you multiply another matrix, like for example, a rotation from the left, then you can think of, well, and before that, maybe the matrix A is just, okay, let me get back to here. So I always call this matrix here, this matrix you can see, I always call this the camera matrix. Because yeah, it just defines what a camera looks like. And the column, yeah, and I think without an intuition for this, it's really hard to understand why would put a matrix on the left or on the right. So this I call the camera matrix, and if you, for example, if this is a 3 by 3 matrix, then here the first column is the x-axis. Oh, you can't even see what so this, I meant this matrix here. This here I call the camera matrix, or I mean probably other people call this way too. And the like if it's a 3 by 3 matrix, the columns represent the axes of this coordinate system. So for example, the first column is the x-axis, the second column is the y-axis, and the last column is the z-axis. And with that, you can always imagine, yeah, what this matrix looks like. And also, if I call this matrix C, for example, so this matrix here is C, and if I now have a rotation matrix and I multiply this from the left, so for example, let's say this is a rotation around the x-axis, or let's say it's a rotation about the y-axis, so this green axis here. So what is left from, wait, well, I meant right multiplication. I mix these up sometimes. So what this left right multiplication does is it rotates in the local space of this coordinate system. So I'm not sure how to visualize this, but it would not rotate around the global y-axis, which would lie here, because this is the global y-axis. But this right multiplication transforms it in the local space. So it transforms it around this axis here. So right multiplication what this does is like local transform. And now you, oops. Now maybe you can already guess what the other rotation might do. So if we multiply this rotation matrix from the left, then we rotate around the global axis. Yeah, and that's one thing how you can imagine what these transformations do. So left multiply, and this is a global transform. And you can even like think about why this happens. because if we multiply this from the left, then this matrix was already applied. So everything is already in global coordinates. You can think of it this way. So then this, of course, just rotates around the global coordinates. However, if we multiply this from the right, then this matrix was not applied. So you can think of it like we don't even know that this matrix exists. So think of it like this is the original coordinate system, because later that is the coordinate system that we are looking at. And when you multiply it from the right, this is the first thing you do. So of course you rotate around the local coordinate system. So I hope that wasn't too confusing, but that's what I think about. Yeah, so that's one important thing to keep in mind. Okay, so let's see. Maybe I can even make an example here. So if we rotate around the x-axis first, I think this should be correct. Right. Yeah, so you can even see what I meant here. So first we rotate around the x-axis. So the x-axis points in this direction here. And so when I move up and down, we rotate around the x-axis. And now if it's already a bit rotated, after that, we rotate around the global y-axis. So you can see like it rotates around this axis here, like the global y-axis. And if we change the direction here, the order, um, yeah, this is what I meant. So if I now rotate around the x-axis at first, it works, but then we rotate around the y-axis in local space. So this is why when I now turn my mouse this way, it doesn't rotate around the global y-axis. It rotates instead around the y-axis that is in this rectangle, and you can see that. I hope. Okay, so yeah, and the next thing that maybe is important to understand this is translations, because we don't just want to rotate the camera, we also want to move the camera. So we somehow need to add to this description here, we somehow need to add an offset. So because like we want the camera to be at some, maybe I could use a different color, some offset here. And this is why often instead of 3x3 matrices, 4x4 matrices are used. And 4x4 matrices look like this. So in the upper left, we still have the original 3x3 matrix. But additionally, we also have this translation vector here, which is in the last column. And then we just fill this here with the zeros and the last one with a 1. And yeah, so that's what the camera matrix will look like. So the translation vector, where the camera is exactly located, is in this column. and the axes in which direction the camera is looking, so to speak, are in this first upper left 3x3 matrix. And to make the matrix multiplication work, I mean, because it's not possible to multiply the point like x, y, z with this, because if we were to multiply this out, we would multiply this row with this, and then this row with this, and then this with this, and this with this. But this doesn't work because here are 3 entries and here are 4. So this is why homogeneous coordinates are used, which basically just adds a w coordinate to the point. So for example, x, okay, maybe point x, point y, point z, and then we also have a w coordinate. And if you think about what this actually means, because all this matrix does, it multiplies the upper left. I mean, I could write this out, but it takes a bit of time, so I'm just going to explain what is happening. But if you wanted to like get an idea what is exactly happening here, you could write the matrix multiplication out, and then you could see what is exactly happening. But if this is, for example, the rotational part, then what is happening here is we multiply the rotational part with the point and add the t vector times the w component. And this is why often we just choose this to be 1 or 0. So 1 in the case if we want to translate the point, and 0 in the case if we don't want to translate the point. So with the w coordinate, you can kind of think of it like, do we want to translate the point or not? And for example, you don't want to translate normal vectors because yeah, that would make them look weird. Yeah, so normally with normal vectors, you use a w coordinate of 0, and with positions, you use a w coordinate of 1. Yeah, but that's the basic idea of what this matrix looks like. And yeah, so now we can maybe I will already write a few functions that converts these 3x3 matrices to 4x4 matrices. So previously we just had this M3, which represents a 3x3 matrix, but I think there's also a 4x4 matrix. And let's see, I want to think about how I want to name these. So I can create a so I want to write a function that converts a 3x3 matrix to a 4x4 matrix. So, and the confusing part is now how I access the elements in this eigenmatrix, because I'm not sure. I think I will also define a vector 4, and then what I will do is just, this is probably not very efficient, but I want this to be correct first. So first I want to create an identity matrix. And then I can push these vectors into the 4x4 matrix. Like this and like this. And now I can... Okay, so this would probably be way easier if I was more skilled in using eigen, but I am actually... I'm a real noob. But I think we can just use this operator here. Because with this operator you can access like row and column. I'm not even sure if this is row or column, but we will see. So I want to copy all of these. Okay, and now I want to test this function. Maybe it works. And maybe remove the other output. Um, Wait, I should probably move the rectangle. I think that looks correct. So we have the rotation matrix here in the upper left, and the other components are like they should. So no translation, and yeah, the last column is just 0, 0, 1. Okay, maybe we can even test this. So we can, because we can send the 4x4 matrix directly to OpenGL. I just forgot to open the shaders. So previously we had the matrix 3 here, and now we can, because I changed this to a matrix 4, I want to change this here too. However, for that, the point needs to be, like I said, the point needs to be a 4 component vector. So we need to add an additional W component. And in this case, I want to check, I want to verify that the matrix here works. So I want to add the offset that is in the matrix. So I put a 1 here to add the translation. And so right now this should change nothing because the translation vector is 0. And yeah, so because the result is also a vector 4, I need to remove the W component, which I just will do now with this here. So in GLSL, you can just append the components you want to have as an member. So this works. And yeah, it was like before. And if I, for example, if I overload this function now with a vector, with a translation vector, that may, for example, be the 0 vector by default. Let's see if this works. Okay. So yeah, I don't know. This is probably possible in many programming languages, but you can define an additional argument and then just set it to be like a default value, and this way you don't have to input the last argument, but you can specify it if you want. For example, I just want to translate the rectangle by a small amount in the x direction. And then I need to also add this. Maybe this works if I put this just here. Nope. Okay. Maybe this works. Okay. So what I've done now is I put the translation vector in the last column of the matrix. And of course, the last position is still 0. And now you can see that the rectangle is not exactly aligned because I moved it a slight bit to the right here, because the translation vector is like it's 0.1 units moved to the right. Yeah. And additionally, I want to create a function that creates a 4x4 matrix that just rotates, that just translates any, that is just a translation matrix. So similar to this function, but I just want to, okay, maybe I can set to identity. Matrix. Okay, maybe this works. Like I said, this is not going to be efficient. But if you were to write this yourself with like not the eigentypes, which I just used to make to have multiplication functions and so on, you I mean this would be very easy. For example, you would define a struct M4, and then you maybe just would put an array inside of here with 16 elements, for example, and then you could just set them individually. But I don't know. I'm like it's a bit hard to input these elements. I guess this could work. I get always confused by this, so um yeah, I don't know. Hello, Snowjang. So I want to create this matrix here, and maybe if I just do this and then identity, this works. Okay, this seems to work. And now I just need to set the last vector. So I think this is I mean, it's probably going to be the row and then the column index. You have also tried to make a physics engine from scratch. And did it work? Okay. Oh, I see. But that's even more difficult, isn't it? Because um, you need to use all of these blocks. How is it even possible? um, okay, so now I just used the translation matrix here, and you can see it still works. So I assume I put this in the in the right spot. Um, okay. So I think. Oh, okay. Yeah, in 2D it's maybe easier. That's nice. And the last thing I want to do is to make a scaling matrix. Um, that just scales the axis, like scales everything uniformly. I think I can just multiply this. So what this matrix looks like is instead of ones here, it has like scaling factor then. Um, are you talking to me, Rezo? So, and if I use this scale matrix here, The rectangle should just get smaller. Whoa. Okay, maybe that doesn't work. uh, I see why. That's even worse. What's happening? ah, again. Okay, so now you can see the rectangle is smaller. And with all of these three functions like scale, rotate, and translate, we can now create the first step of the transformation pipeline. Um, so, hello. I don't know what the Featherstone algorithm is. So now the first thing that we want to do is to transform this image that you can see here into this image. And like I said, this here is the camera matrix. And if you think about it, this here is then, wait. So this here is the identity system. This here is the camera system. And if you think about it, what multiplying a point with this matrix here does, for example, if you have a point like relative to this camera that would look like this here, then if we were to multiply this point with the camera matrix, then we would transform the point here into the global coordinate system. But that's not what we want, because we have the cube, and we want to transform the cube from the world coordinate system into the camera coordinate system. So and what a multiplication by this camera matrix does, it transforms the point from the camera system to the global system. But we want exactly the opposite step. So you can imagine that we want to do exactly the opposite. So we want to multiply everything with this matrix here, because this way the cube is given, like for example, this point of the cube is given in this coordinate system, and then we want to multiply it with the system. Let's say this here was the matrix V. And if we multiply this point, P for example, with V, then we get the point in view space. So then we have the description that we actually want. Because this point here, or this, I don't know, is defined in the global space, but we want to have it local to this space. So these are in correspondence here, these two systems. But of course, they are not the same. They are just in a different coordinate system. I don't know if this was confusing right now. So what we actually just want to do is we want to multiply our point with the inverse of the camera matrix, because we don't want to move the point from the camera's point of view to the global point of view. We want to move it from the global point of view relative to the camera, which is this transformation. And this is why I even came up with the camera matrix. I mean, I didn't came up with it because this is why I talked about the camera matrix. because the camera matrix is the inverse of the view matrix. So the camera matrix is the inverse of the view matrix. And working with the view matrix with this, which is this here, this coordinate system, is not very intuitive, I think. I mean, it's again, it's just a coordinate system relative to this coordinate system, but it's not really intuitive. I think it's much more intuitive to work with the camera system. But if we have a description of the camera system, so if we have this given, we can just compute V by using the inverse. So V is the inverse of the camera matrix. So essentially, to do this step here, to convert this image to this image, we just need to multiply our point with the inverse of the camera matrix, which is the view matrix. But, and that's something I learned so I didn't know this from the beginning is what I wanted to say. If we know how to construct the camera matrix, we can easily construct the view matrix as well. So for example, no, let's go back here. So let's think about what this camera matrix should actually be. Maybe I can copy this here and move it to here again. So again, this is the original coordinate system. And we want to have the camera coordinate system. And if you are using, for example, yeah, like I like to use a centered camera, like a camera that just focuses a single point and you can rotate it around it or scale onto the point, like similar to how you do this stuff in Blender. I don't know how long this will take. Okay, so in Blender you have like this focus point here, and you just rotate your camera around this point, and you can also zoom everything. And yeah, so that's what I want to construct now. So this type of camera. For example, another type of camera would be something like an FPS camera, like in a first-person shooter where you just move your head and then the direction. So it's more like a direction where you look at. But here, so we can, because we can, the reason I just wrote these functions here is we can construct the camera matrix out of these functions here. So the first thing, because initially the camera matrix is just the identity matrix, like this. And now we can apply different matrices to this camera matrix or different operations to convert this into the camera matrix. So for example, the first thing that I like to do is just move the frame, like with the translation, move the frame to the radius you want the camera to be, like the distance you want the camera to be from the center point. And this would look like this here. So first, maybe I need a little bit more space for this. So the first thing I want to do is translate the camera. And I just want to translate in the Z direction because the camera will still look in this direction after the transformation. Um, so I want to wait, translate. I don't want to translate in X direction. I don't want to translate it in Y direction. And I don't want to translate it in, wait, I want to translate it in Z direction. So here I input the radius that I want the camera to be the distance from the center point. And next, and again, now you can think the next thing that we want to do is to rotate the camera around the center point. And again, this is where the stuff that I told you in the beginning with the left and right multiply is important. Like we want to rotate the camera around the center point and not around its local point here. It's around the coordinate space that we currently have. So of course we need to do a left multiplication because that performs a rotation around the global coordinate system, which basically means that we rotate this around this big circle here. Instead, if we were to right multiply this, we would just rotate the coordinate system around its local center point. Yeah. So now I just need to think a bit about which rotation I want to perform first, because one is not intuitive. Okay, so I I want to rotate around the x-axis first. So basically, we perform a rotation around this big circle here, which is, so the circle is perpendicular to the x-axis. And so let's write this down here. Rotation. I will just write this down like here. And this, I will just call this angle x. And yeah, so what this will do is it will, like for example, if this angle is, for example, here, if it is this angle, then we will look from this direction at the center point. And the next thing, because we also want to move the camera in the other direction with the mouse, the next thing is we can rotate it around the global y-axis. So in this case, we then rotate around this circle. So here I can write rotate z, and then angle y, rotate y, I mean. Yeah, so that's basically, I think that's enough for now. Let's see. Wait a second, I need to look something up. Yeah, okay, so if we wanted, we could also scale everything at the end. For example, by a zoom factor. Yeah. So let's implement this. Wait. Okay. So this will be the camera matrix. Let's call it C. So again, the first thing we want to do is translate. And then we can define the camera radius. For example, 6 meters. And then we can perform a rotation, like here. So the first thing we did was translate, then rotate around the x-axis. And again, we can just use our angles here. Angle x. And the next thing is the rotation around the y-axis. Rotation y. Angle y. And lastly, we could make a scale here. We could define a zoom factor. For example, 2. I don't know. I'm not sure. We need to check this later. So this is the camera matrix. And unfortunately, I can't yeah, I can't test this right now because, like I said, we need to implement all steps of this transformation pipeline. But yeah, so first translate, then rotate x, then rotate y, then scale. But because, like I showed you, we don't need the camera matrix. We instead need the view matrix to transform our points. And this is the nice thing about it. So if you didn't construct this like this, for example, if you just had the camera matrix and didn't know how it was constructed, this would be a bit difficult. You could just write an invert, a function that inverts a matrix. But we can make this a little bit easier because we know that if we multiply many matrices together and invert them, this is just equal to like flipping each of them and applying the the inverse to each of them individually. So yeah, this is what we can do now. So basically, to get the view matrix, the only thing we need to do is flip each of these here and invert them. So what does look like? Translate 0, 0, minus r, and then rotate x minus angle x, and then rotate y minus angle y, and so on. So scale 1 over zoom. And then we have the view matrix. So let's define this too. So first the translation with the negative radius. Then we take the x rotation with the negative angle. Then we take the y rotation with the negative angle. And lastly, we just invert the scale. So that's the view matrix. I think this is really cool because when I started this stuff, I didn't want to write an a function that inverts a matrix because that's I mean it's just horrible. The code is I mean yeah, it's just a bit cumbersome to implement a function that inverts a matrix. But like this, you don't even need to invert a matrix, which is really nice, I think. And now we could, in theory, make this here, make another uniform variable, and we could, like for example, call this the med v. Um, and then we just take the data of it and put it into the shader. And to now do the first step here, yeah, we just multiply our point with the view matrix. So instead of this R here, for example, we use V. And yeah, so that's the first step. Unfortunately, like I said, I can't show you this because I don't think we will see anything. And I made some errors. Translation. Oops. Met V of course. Yeah, so we don't see anything because we don't have a projection matrix right now. Yeah. So this is the next step. So we have this here now. We have done this. So now we need to apply the view frustum. And yeah, I had a picture of this in the beginning. So basically, we have this view frustum here. Maybe this picture is even a bit better because everything is now. So this is our view frame, and this is the initial frame now because we already did the view transformation. Basically, we now define this view frustum here and want to convert it into this NDC cube. And I mean, you can even think about why this is a reasonable thing to do. So if you are probably sitting in front of a PC right now, and this is kind of like looking out of the window. So you are here. And I mean, you have two eyes, okay, but let's just assume you had one eye somehow. And so then everything you would see is just you connect your eye with the corners of your monitor, for example. And then you can see that you would get this view frustum here. Because, of course, you can not just see everything. Like nothing is cut off if at the edge of your screen or of your window, for example. If you look outside, you can, of course, if you stand in the middle here, you can of course look at a little bit outside, and this is because the view frustum increases here. Yeah, but that's basically the view frustum. And if you would do this 100% correct, like for example, I assume you would have to do this if you were doing VR or something, or well, I don't know. So if you were to do this 100% correctly, you would have to take the position of your head into account, and like the angle, like how large your computer screen is, and everything. So it would be a bit complicated, and there are actually functions you can write to. So what I want to tell you is there are two ways to define a view frustum. The first way is to make this kind of really correct, is you define a function that takes like the right position, so right, left, top, bottom. You assume that this point is your origin, 0, 0, 0, and then you define the the position of the edges of your computer screen, for example, with these variables here. So the right would be here, the top would be here, the bottom would be here, the left would be here. And then you can construct the correct view frustum. But because we don't track the position of the head and make a lot of other simplifications, we will use the second option to define a view frustum, which is we just define the field of view angle, and we define, so this is basically this angle here. If we look at this here, or at this here from the side, it looks like this, right? So here are we, and the first parameter here is the field of view angle, and it's the field of view angle in y direction. So this angle here. And like I said, if you would know the distance to your, like the position of your head and the position of your monitor, you could, of course, compute this variable here with some math. But because we don't know all of this, we just assume this value to be, for example, like, I don't know, 80 degrees or something. And the second thing that we want to use to define this view frustum is because, of course, the monitor is not square. The monitor looks like this. The second thing here is a aspect ratio factor that basically just tells you. So, and this is the thing I have to look up because I always forget this. So this is the code of my game currently. And you can see here, so this is the aspect factor. Okay, it's width over height. So basically it tells you just, so this is the width of your screen, this is the height of your screen. Whoops. This is the height of your screen. And so the second factor is just width over height. So that we can correctly define the view frustum. Because if we don't know the aspect ratio and we only have the field of view in y direction, we don't know how wide the monitor is, which is important for the view frustum. And the second thing is because we are using OpenGL here, or like I mean it's done in any other graphics API too. We have to convert this view frustum into this cube, and this cube here has bounds, like you can see here. So we define a new plane and a far plane that which are mapped to these bounds here. So in the end, the near plane is mapped to this distance, and the far plane is mapped to this distance. So these would also be need to be defined here. Okay. So now, and like I told you, I want to use this because it's a bit easier than using this here, and it's also so it's easier to define the variables here. Like if you just sat in front of your computer screen, like you would wonder, I think, what is R, what is L, what is T, what is B, what is B. But when using this description here, it's a bit easier because you can just assume, okay, you assume your distance would be some amount of centimeters, and then you can just assume this to be, for example, 80 degrees or something. And this you can just compute. It's really easy. And these you have to, think about. This is basically a choice. So now that we know how our view frustum is defined, we can take a look how we can convert this description here into this description. And that's a bit tricky. So basically, I will draw this now. Again. So this is not entirely correct. And maybe I can do this like this here. So let's start here and maybe go 4 parts into this direction and here. Well, okay. So we have the coordinate system here. Can't you just use... Yeah, so the x and y values are a bit easier than the z, and I'm trying to derive the stuff that you just wrote down, basically. um, so we have this angle given here. This is field of view y, and we want to convert this into the cube. I hope this is a cube. I'm not sure. Maybe this is a cube. And in the cube, we are looking from this direction here. But the origin of the cube is in the middle, in the center. And also, so this is NDC. Also, the cube is a left-handed coordinate system, which is really weird, but that's just how it is. And each of the corners here is 1 or -1. So this is 1, -1. Okay, maybe. So this is 1 here, -1. And this is 1, -1. So let's say we have a point here. And let's focus on the y conversion right now. So you forgot what? So let's focus on the y here. And this is where I need to think a bit myself. So basically, the y is this here, the y of the point. And okay, so what we need to do is we need to figure out the height at the view frustum here at this point, because then we can just, if we know that this is the maximum, then we can just divide this here by this, and then we have the point in a range from -1 to 1. So basically, because we know, we want to know this height here. So this is our unknown. And what we know is that the distance here, this is the z coordinate of the point. And now you can see this is a right triangle. And this angle here is field of view. So field of view, wait, this is field of view y half. So I don't know how you remember trigonometry, but I will always remember this like here. So if this is our triangle, and we have the hypotenuse, the so the adjacent side, and now this would be the opposite side, but because in German this is called the Gegenkathete, and so this is why I named this G. And I always remember these formulas by saying this, and this here. And what is basic, so I just remember these, and what it basically says is that the cosine of alpha is equal to the adjacent side divided by the length of the hypotenuse. And for the sine, it's pretty similar. It's just the Gegenkathete. And for tan, it's yeah. So basically, this is the numerator and this is the denominator. And this is everything I remember to remember these formulas. So what this means is now we have our angle here, and we want to find the G. And we have the A. So we don't have H. So this way we can, yeah, we can use the tangent, I don't know how this function is called. So to compute G, we just reorder this formula here. So G is equal to tan of alpha times A. So what this means is that this side here, this question mark, is equal to tan of half field of view times Z. So this is the length of this side. Okay, so okay, wait. So let's write this down. So you use so sine upon okay. Yeah, I guess it's almost the same. It's just that you don't remember, like you discard these words here, and then this is the opposite side, right? Yeah. Yeah, okay. I guess this makes sense too. Okay. So, and now let's remove all of this. Now that we know the length of this side here, we can just divide the y coordinate of our point by the length of the side, because then we have, so basically we just normalize this by dividing by this. Because I hope you can see that if we divide by this side, by this length, we normalize, but this point is then 1, and this point and here is then -1. So this is the correctly mapped version into this range, and basically in this range. Yeah, so that's how we do a perspective projection of our y coordinate. So basically y ndc is equal to this. And now you can maybe already see a problem that we have, because this is equal to y. So this is not a problem here. We can just use like 1 over the tangent, 10, I don't know, 1 over 10 of field of view y halved times y. But the problem is we have to divide this by z. And if you know matrix multiplication, which is a linear operation, this is not possible, because our projection matrix will look like this. So it's normally not possible. Of course, somehow we are going to do this. Um, let's think about this. So the projection matrix, initially it might look something like this. And now we already have the scaling factor for our y. So this is the scaling factor for our y. We can write this down here. 1 over 10 field of view y halved. So this is the scaling factor of our y. The only problem is now that we need to divide by z. And Oh, also, what I forgot to mention, we need to divide by negative z, because of course we assume, because this axis points in this direction, so, but we want to have the positive length of this axis, and because if the point lies to the left of this, the axis will be negative, and to make it positive again, we divide by negative z. Okay, so again, we divide by negative z, and this is again where we want to use homogeneous coordinates, because this way what we do is we put a -1 in here, and what this will do is if we multiply a point with this matrix, and for example we put a 1 here, what this will do if you multiply this out, so basically this row times this row, which just results in x, then this row times this row, I'm skipping this part, and lastly, also this is removed here, so we convert this 1 here to the -1 here, and what this results in is then that this row is multiplied by this row, so here we have negative z, and then what OpenGL does, this is not what we have to do. Basically, to convert this form of our point back, maybe you could call this the projection step. We, in the end, we divide by the z, by the w coordinate to homogenize, or whatever you want to call this. So to convert the point back to its 3 vector form, we just perform, so if the point would look like this, dehomogenize or something, we divide by the z, and this way we achieve the scaling factor by the z. So this dividing by z here is possible by putting a -1 in here. Okay. So that's the scaling for the y. And the x is pretty similar. You can imagine if you would like make a top-down version of this diagram here. The only difference is because your points because you have a different scale in the x direction than you have in the y direction, you have to multiply or divide this factor here by your aspect ratio, and I'm not going to derive this because this would be quite unnecessary, but it's basically the same. So I'm not sure if you have divide or multiply with this, but if we had some more time and would just write this down, I think this would be quite easy to see. The only thing is I always forget if you just have to divide or if you have to multiply with this. Okay, so it looks like this. Hello, the macaroni gun. Okay, so the tangent of field of view y halved, and now we have to multiply the denominator by width over height. Okay, so this is basically the conversion of the x and y. The only problem left is now the z. And the z is a bit more difficult because you can imagine if you were to just divide your z by z, you would just get a constant. And what you can instead do is just solve for the correct conversion. So imagine you had these two variables here, because the z should not depend on the x or y. It should only depend on the z itself and maybe a translation of the z. So you look at these two unknowns here, and we want to find these unknowns now. Maybe I need another page for this. So if I paste this here, so how we can solve for these is by just writing down the transformation that is happening. So we have our original z coordinate that is first scaled by a. I mean, you just need to multiply this row by this column. So the x cancels, the y cancels. We just multiply a by z, and then we add b. And finally, in the dehomogenization step, or whatever this is called, we multiply by minus z. And this is basically what this transformation does here. Okay. X, Y, Z, W. And this is the final z coordinate of our point. Like this is z NDC. And like shown here, this here is the far plane, and this here is the near plane. And we want the far plane to be mapped to this here. So the far plane should be mapped to 1. And the near plane yeah, that's true. So this is just 1. Exactly. Thanks. So we want the far plane to be mapped to 1 and the near plane to be mapped to -1, like you can see here, because this is the transformation we want to do. Like this is what OpenGL wants us to do. So if we plug this in here, because we have now two equations. First, we want the far plane. And again, the far plane, so f far is a positive value. And I think I don't want to make a mistake. Yeah, so far is defined to be a positive value. However, if we look at this in this direction here, from this diagram, we can see that this far here is actually minus far. If we look at the z coordinate. And here, this is then minus near. So we have to plug in minus far here, plus b divided by minus z. And that should be equal to 1. To 1. And again, I hope I don't make a mistake. Yeah, I think that's right. So this is the first equation. We want the z coordinate of our in NDC coordinates to be 1 at the far plane. And the second equation is we want the near plane to be mapped to -1. So here minus near plus b and divided by z. And now you can now we can solve for a and b. Yeah, I don't have this prepared, so this might get a bit painful. Oh, and also, of course, this just results in far, and this one just results in near, because the minuses cancel. So we can also rewrite this a little bit. So this is minus a plus b divided by near, and this is minus a divided by what I this is minus a plus b divided by far. So, and now I'm not sure if I should solve this now or if I should just present you the solution. Well, maybe I can solve it. So from the first equation, we can see that a is equal to b divided by far minus 1. So because if we move a to this side and the 1 to the other side, and this we can now insert into the second equation, into this equation, and then we see that solving is more fun. Okay. I mean, yeah, I just hope it isn't boring. So minus 1 is equal to, if we insert a here, minus b divided, and I potentially make a lot of errors. So let's not make errors here. So this is minus b divided by far, and then plus 1 plus b divided by near. Okay, let's see. So we have minus 2 equals minus b far plus b near. And this is then minus b near far near plus b far near. So I'm trying to get the b's onto into one fraction. And because now, so I multiplied this fraction here by near divided by near, and this fraction here by far divided by far. So now they have the same denominator, so I can put these together. So this results in minus b near plus b far divided by far divided by near. Now I can extract the b's. So b far minus near. And also I can move this here. Whoops. Far divided by near. What? Okay. Okay, and now I just want to get the b, so I can multiply. So I can invert this and multiply it. So this results then in minus 2 far near divided by far minus near. So that's b. And maybe I can even look at if it's correct. So So this is the B is the TZ here. And I defined this here to be, okay. So 2 times near times far, this seems to be right. And I have far minus near in the denominator. Okay, so I can swap these. Basically I can distribute to minus, I think, to the denominator, and then I just have far near, near minus far. And that's basically what's here. So that's a result of B. Another painful part now is to reinsert this into the equation for A, or basically just now solve for A. So B, let's write this down here. So if we use this equation and now insert the B here, we can see that 1 is equal to minus A plus okay, this is a bit ugly. So basically 2 far near divided by far from here, this far, and then this near minus far. This far cancels. So what we are left with is A is equal to 2 times near divided by near minus far minus 1. So again, checking. So this is not the same. Hi, Yoga Master, by the way. Or is it Loga Meister? I don't know. Yeah, I don't have a Discord. I maybe I should create one. I was thinking, so the thing is, I don't want to manage a Discord server, but it's probably helpful to discuss things. So yeah, maybe I should create one. Okay, but let's finish this here right now. So we can expand this. Okay, 2 near minus near plus far, near minus far. So basically I just turned the 1 into this fraction with the same denominator as numerator. And then again, I can collect these numerators here with the same denominator. And this way I can just near, so then subtract the 1 here and remove this, plus far, near minus far. So this is the result. Okay, so Yoga Meister. Okay, nice. And this is far plus near, near minus far. Okay, so this equation is correct too. Very nice. So basically that means we are done with the derivation. So this matrix here, if we write this down a little bit larger, is 1 divided by tangent of field of view y. divided by 2. And again, the x needs to be divided by width over height. Then the y factor is tangent, field of view y halved. And then a, we just, here, this is a, near plus far, divided by near minus far. And then b was just 2 times near times far divided by near minus far. Yeah, so is cotangent the inverse of tangent? I'm always confused by these functions, but you might be right. So tan cotangent. Wait, that's a German page. Well, but this is the only important thing. So yeah, you might be right. Okay. But I already wrote this down now. But thanks for the tip. So 0, 0, 0. Okay, so that's a projection matrix, which we can implement now. So static. Again, it's a 4x4 matrix, perspective, and it's called a perspective projection. I don't know if you said that. Another way to do a projection is by using an how is this called? An orthogonal projection. So basically in Blender, I think if you press 5, yeah, so this is an orthogonal projection. You can see that regardless of how far something is, it appears the same. So it's the same width regardless of how far it is. And that's the definition of a perspective projection, I would say. And the perspective projection, of course, defines this frustum which gets scaled if it's far away. So basically, this is a perspective projection. And what an orthogonal projection looks like is just a cube, like here. But this cube has different bounds, like this is left, right, top, bottom. So then we have to just map this cube to this. But that's not what we're doing here. Okay. So first of all, we need the field of view y angle. Then we need width over height. And we need the near plane and the far plane. And I think in this case, I will just use this weird operator here. So looking at the matrix, first let's compute the tangent of the half field of view angle. Field of view, wait. field of y divided by 2. And yeah, so then the scaling factor of the x value here is just 1 over the tangent times width over height. And the scaling factor of the y is just the same without the, whoops, it's just the same but without the width over height thing. And then again I can call these a and b. So a was this vector here, that's near plus far divided by near minus far. And then b, okay, this is, wait, here, this is 2 times near times far. Divided by near minus far. Okay, and now I can input these here. So x 0. This is really strange. S, y. And now again 0, 0, a, b. And here is now the minus 1 and 0 again. Okay. So that's the perspective projection function. So if we call this here scale maybe let's call this p, and this is in radians probably. So 80 degrees radians. This is really ugly, but I don't think I have a definition of pi here. So yeah, width over height. Okay, this is another tricky one. Okay, if I don't rescale the window, I will just use these here now. And I want to make sure that I don't divide an integer by an integer. And then the near plane would be, for example, 1, and the far plane like 100. So why this matters is, first of all, because of precision. So like if you, okay, so first of all, this value here, everything that is behind 100 in this case, so let's say here was a cube, but the cube was positioned at minus 200. The cube would be cut off here and would not be visible. Yeah, because it's mapped here. So in this view here, the cube would lie here, for example. And yeah, that's really bad. So then you could say, okay, well maybe I just increase this to a very large number. But the problem then is that the space in between, So of course, floating point only has a specific precision. So the space here is limited. And if you choose the range too high, then you get Z fighting. Where basically objects that are really close together then fight for the Z value, which is really bad. Yeah, so you have to pick reasonable numbers here. Yeah. And now the last thing we need to do is input this into the shader. And then we need to pray that it works. What the hell? So I want to create a transform point. Let's call this P4. I want to store this here because we need to input this into GL position. Because in the end, the OpenGL does the perspective division. And this is why we need to put this here. And then we can just use this as well. And then now we need to pray that I didn't make a mistake. Wait, I'm confused now. Do I have to divide this myself? Oh, I forgot the 4. And okay, that's a good sign. We can see something. And we can even rotate this. Nice. First try. Lol. Okay, very nice. So the last thing I want to do maybe is make a zoom. So mouse wheel or something. STL mouse wheel. Okay. So the type is mouse wheel. STL mouse wheel, right? And now wheel Y. Okay, I think I use Y scrolling. So if I scroll the wheel up, and I'm never really sure. What to do in this case. I would just try to scale this by like 1.1f. And in the other case, I would try to scale it by the inverse of that. So basically divide this. And now I can remove this. Okay, I would say that's the wrong direction. Um, okay. And also I think the scrolling direction is in the wrong direction. So wait. Oh, okay, but this works now. Okay. So that's basically it. That's the transformation pipeline. I mean, it still looked kind of boring, but in theory, we could now add like a plane here and cube, and then we are almost at the result in the thumbnail. um, but I don't know. The stream is very long, so I think I might do this in the next stream again. You should just use. Yeah, it's really magic. What commands do you mean? I'm not sure. Magic. I would really like to use a cube here, but this is probably. This is really painful. To create a cube out of this. Well, maybe the zooming factor doesn't work like I want it to work. Whatever. So what commands do links show? You mean if you post a link in the chat? Sorry, I'm not sure what you mean. All right. Okay, maybe I can spend another painful 10 minutes to make a cube out of this, but yeah. Or maybe just add another plane. A cube is very painful. Nope. Unfortunately, I'm just pasting the vertex data in here. It's really simple. um, so okay, you said I could use just for the commands. You can I have never seen this before. And I'm definitely not going to to use Vulkan. I think then I would make a stream that's like a week long. Okay, so like what is this even called? Just just like program just or something? Um GitHub. Ah, oops. Just a command runner. Wait, so is this like a build system or I mean, I think Vulkan is very well supported. Probably not on PCs that are like 20 years old, but the problem I have with Vulkan is just that I would need to write like 500 lines of code just to get this triangle that we just saw. And that's really painful. Okay, so let's see. So I think if I just copy these here, uh, -5 and 5, 5, and then 5, -5, -5, 0, 0, 0. Hmm. Wait. Okay, we have 12 vertices. Yeah, okay. Yeah, but for example, on Mac, you have to use the translation layer to translate Vulkan calls to metal, which is stupid. But you don't have to do this by hand, do you? I have no idea. But that sounds terrible. I just recipes. I think you know a lot more than I do. So I don't know. I will take a look at this. At just. Um, but I am not sure how to do this right now. So the last thing I want to enable here is depth testing. Enable depth. I don't know how to enable the depth test. All right. Okay. Okay. Yeah, I would watch the tutorial. I mean, I'm subscribed to you anyway, but so I need to clear the depth buffer. Depth Wait, yeah, have alphabet. Okay. So now we have a ground and one side of the cube. So yeah, um, yeah, I think I will leave it at this for the stream. And I think Vulkan is less stable than Direct3D on Windows. I don't know, I can't tell you. But it might be. I mean, it sounds like it would make sense because Direct3D is developed by Microsoft. All right. Um, yeah, so okay, so how hard is it to create a Discord server? Can I create this right now? What do you think? Okay. Hello, Illuv Soup. Thanks, that's nice to hear. Yeah. It was quite a bit of math, but the thing is, when implementing papers or something, then I would have to explain a lot of math. So that's what these streams would look like. Maybe it's a bit boring, but yeah, I don't know. Is this in C or C++? Um, mm, so the reason I'm writing C/C++ is because I'm using C++ because of operator overloading. But if I could, I would actually write this in C because I don't know, I don't like how modern C++ looks. So yeah, it's a mix of the two. Um, that's great to hear that I've inspired you to make your own engine. Um, yeah, I don't know. Maybe I can create this Discord server right now because else um, I would have to make an announcement again. I don't know how complicated this is. Let's see. But for the program, I'm basically done for today. So that's everything. I will just try maybe to make a Discord server right now so we can already join. Um, let's see. Wow, that was fast. But so if I post the link right now, there's no, I have not created any rules or something. Well, there isn't anything on the server anyway, so I will just paste the link right in the chat here. And if you want to join, you are welcome to do so. Okay, cool. Yeah, hello. Okay, so then thanks for watching the stream and thanks for participating. Yeah, I will see if a few more chat messages come in, but basically I'm done now. Okay, bye. Oh, wait. It would be cool if you wrote a preprocessor to the operator overloading for you, then you could just, yeah. And I thought about that, but I don't know. It was, it's probably a bit of work, and I'm not experienced in writing compilers or even or preprocessors, so I don't know. It would just make it harder for other people to use the code because then they would have to somehow run the preprocessor. Um, I don't know, but in theory, yeah, that's a good idea. All right.